things. So yesterday we did the definition of linear transformations, which I know some of you have been working with and really struggling with. Continue, those of you who are working, don't just ignore it. That definition of linear transformations is very important, and you do need to be able to work with it. So do continue your struggles. You will be victorious, I know. Proving that something is not a linear transformation is much easier than proving that something is, because all you need to do is find a counterexample. But proving that something is a linear transformation is always a little bit of a pain. But there you go. It's doable. An important, a powerful characteristic of linear transformations is that we can represent them in function form, but we can also represent them as a matrix product. And that's what I'm going to start off looking at today. That the action of t on vector x, so that's function notation, can be written as some matrix times by the vector x. Okay, your calculators are not going to write your exam for you. I'd recommend putting them away. Not calculators, phones, whatever those things are you're holding in hands. Your electronic devices are not going to write your exams for you, so please put them away. It's probably easiest to demonstrate with an example rather than a whole lot of wordy writing. I'll do exercise 58. It says, given the transformations in function form, find the matrix which represents them. Okay, so number A, it says x plus 2y, x minus 4y. Okay. Where, and I think this is something that people didn't pick up on yesterday when I did the, please keep quiet, when I did the definition of linearity, I wrote something like this. I said t of, it wasn't actually the definition of linearity, it was that one exercise, that first one. It says t of x equals 2x, x plus y. That assumes that that vector x looks like that. That's the assumption. Then in my proof, I went on and I defined two vectors. Well, I called one x and I called the other one y, and I called the components of the x vector x1, x2, and I called the components of the y vector y1, y2, and then it really confused people because they couldn't see how those x's from the one vector and the y's from the other vector were somehow not the x's and y's that were mentioned here. But here, the x and the y just refers to the first component and the second component. So if I had chosen to call x x1, x2, then t of x would have been 2x1, x1 plus x2. And if I had chosen to call x ab, then t of x would be 2a, a plus b. But the default, so if you just write the vector x and you don't name its components, the default is to assume that its components are xy or xyz. That was what was going on in that exercise, whatever it was, 54. And I know that confused people quite a lot. Okay, so here, once again, this is assuming that the x components are xy. There was a question in the middle there. You're right there, Michael? You're fine. Okay. All right, so that is a linear transformation. We could prove it, but not going to. We have been told, we actually haven't been told that they're linear, but they are linear, and we can represent them in matrix form. So what's happening here is we're putting in a vector that has components x and y, and we're getting out a new vector where the new first component is the old first component plus 2 times the second component, and the new second component is the old first component minus 4 times the old second component. Okay, so we're putting in a vector and we're getting out a new vector. And we can write that as a matrix product. We can invent a matrix A that when we multiply by the column vector xy gives us what we want. And then we just need to figure out what numbers go into that matrix. So you all remember matrix multiplication, I hope. And that's the matrix that'll do the job. Remember how to do matrix multiplication? Okay, you'll take a row of the matrix on the left and a column of the matrix on the right. Of course, the matrix on the right only has one column, and we tend to call matrices like that vectors. So you take a row on the left and a column on the right, and you essentially do a dot product of their components. So it's 1 times x plus 2 times y. And that'll give us the top over there. And then we take the second row and we do a little dot product with x, y, and we get 1 times x minus 4 times y, and that gives us. And that's matrix multiplication. Okay, so that was 58a. B, what is it? T of x equals, what is it? 3x minus y and 2x. So it's going to be 3 minus 1, 2, 0. And C, x must be a 3-dimensional vector by the fact that the letters x, y, and z are all present there. So I need a 3 by 3 matrix, which I'm going to multiply with a 3 by 1 vector, x, y, z. And I'm going to get out another vector, x plus z, x minus y, and y plus z. There we go. So it's going to be 1, 0, 1, 1 minus 1, 0, 0, 1, 1. There you go. You give it a try. Now try number 59. All right, so far we've basically just been treating linear transformations in an algebraic way, like pushing letters and numbers around on the page. But there, of course, is a geometric effect, a diagrammatic effect, if you will, to linear transformations, where what's happening is that there's a point going in and it's being transformed into a different point. So if you think of your vectors as points in space, you can think of the transformation as taking a point and actually moving it to a different point. And it's that geometric effect of transformations that we're really interested in. And what we're truly interested in is not so much what's happening to individual points, but what's happening to regions, to circles or squares, or what's happening to regions when you apply transformations to them. But we'll start off just looking at individual points. So transformations have a geometric, or perhaps you could say visual, interpretation. That of transforming points and curves, because curves are just collections of points, and regions, because they're also just collections of points. Effectively shifting them. Okay, so I'm going to demonstrate with an example, number 60, which is a rather random little example. It's not a very well designed example. 61 is slightly nicer. I've given that one to you to do, but use the given mapping to transform the indicated points, and then actually plot them on a diagram to see how they've changed. Okay, so I've got f of x equals x plus y minus x. So that is the transformation. If I now have 3 points, P, 1, 0, Q, minus 2, R, the origin, and I transform them, I'm going to transform them into P dash, Q dash, and R dash. Let's have a look. If I plug x equals 1 and y equals 0 into my transformation, what do I get? I get 1 minus 1. Minus 2 will become minus 4, 2. And 0, 0, that's a rather funny looking 0. Let me fix that. 0, 0 becomes 0, 0. It is a characteristic of linear transformations that the origin maps to the origin. And if I draw that on a picture, let's have a look. P started off at 1, 0 and shifted to 1, minus 1. Q started off at minus 2, so down here, and shifted to minus 4, 2, so somewhere up here. That's Q and that's Q dash. And R was at the origin, and R dash is also at the origin. Okay, I didn't draw a scale onto my picture because otherwise I think I'll make the picture a little bit too busy. There doesn't seem to be a lot of there are so few points here that you're not really seeing a pattern. If we had a whole sea of points, you'd see there'd be a little bit of a pattern. You'd be able to see a sort of a flow to that picture. As it is with just 3 little random points, it doesn't look like much is happening. I'm just trying to geometrically represent what is happening with transformations. B, as I say, this is a fairly random little example. 2x plus y, x minus 2y, very similar. 3 slightly different points. Once again, I've included the origin. P dash, Q dash, R dash. Okay, I'm going to plug x equals 2 and y equals 3 into my transformation. What do I get? 4 plus 3 is 7. 2 minus 6 is minus 4. Minus 1, 2, so that'll be minus 2 plus 2. It'll be minus 1 minus 4. And 0, 0. Once again, if I draw that, 2, 3 has gone to 7 minus 4. P dash. Q started at minus 1, 2, minus 1, 2, and changed to 0, minus 5. Down here somewhere. And good old R, R dash are both at the origin. Okay, why don't you give number 61 a try? Now, number 61 is similar. There's a bunch of points, quite a few points. How many altogether? 1, 2, 3, 4, 5, 6, 7. 7 points. Certainly in my handbook, the picture is kind of smudged. I don't know whether yours is as well. But anyway, you've been given the coordinates of the points, so you can tell where they're supposed to be. As you can see on the diagram, if you look up 1, 2, 3, 4 of those points make a straight line. And there are also 4 points that make a square. Why don't you transform all of those points, plot them in their new places? I would recommend just draw a fresh diagram and maybe name those points A, B, C, D, and name their transformed points A dash, B dash, or something like that. And see what happens to those lines and that line and that square. Does it remain a line? Does it remain the same line? Does it actually stop being a line and all those dots just end up scattered? What happens to that square? Do those 4 dots still form a square? Or some other well, I suppose 4 points always form a quadrilateral, but would it be a regular quadrilateral? Transform those points, see what happens. Okay, so let me start plotting the points in the image. That, my A dash ends up over there, B dash, what happens? A dash, B dash, C dash. Ooh, I need to move this thing out of the way. There we go, there's D dash. And what happens is that those 4 points that were on a straight line actually remain on a straight line. Oh, it's a different straight line, but they still remain in a straight line. And then the 4 points that made the square, which was C, E, F, and G, I just want to get them correct. Is that one? Let's have a look. That was 3 goes to 6, 0, 6, 0 is that one. So E. My E dash ends up over there somewhere. And F up here somewhere. And that over there I think is G dash. Okay, if I'm not mistaken. Am I right? Which is G? G is that one? It's what? 1, 1, 2, 0, 2, 0. Yes. And so those 4 points that formed a square are now forming a parallelogram. Have I made a mistake? Sorry, have I numbered something incorrectly? Down at the front here and then the back, yeah?
If you're naming the points, does it have to be what you transform? So A has to match
Yes,
the sign.
correct.
So there.
Have I made a mistake? Cool, then I'll fix it. Was that what you're also pointing out? I was just assuming that that's what...
The line is A, B, F, G.
A, B... Let's have a point. That point over there is 1, 3. And 1, 3 ends up at 2 minus 2. I think I'm right. Yeah?
I think the confusion is coming in where people are naming the points as they give it out in the sentence, the ABC.
Oh, I see. Oh, yeah. I just randomly called them this because I just drew my picture and I thought I'll call them names. I see. Perhaps that's what, yeah. Okay, so if you labeled them A, B, C, D in the order they were given in the question, then your A's and B's will be in different places to mine. In which case, my letters will be confusing. Maybe me leave my letters out in anything that you're writing. What I'm trying to demonstrate is the line stayed a line. Became a different line, but it didn't turn into something curvy, and it didn't end up a scatter of points. Similarly, my quadrilateral remained, well, as I say, any 4 points will form a quadrilateral. My regular quadrilateral remained a regular quadrilateral. My square turned into a parallelogram. So this is important. Linear transformations basically keep things general shape. If something's straight, it keeps it straight. The largest effect that a linear transformation, or the most extreme effect that a linear transformation can have on a shape, is to stretch it. That's basically all it can do. It can stretch it. So that square basically got stretched into a parallelogram. But straight things never turn curvy under linear transformations, ever. And curvy things don't go straight. That's too extreme a transformation for a linear transformation. Non-linear transformations do that all the time, but not linear. Linear, straight things remain straight. Okay, and that is very important. That turns out to be a very useful... Linear transformations altogether are incredibly useful and powerful things. And that is one of the useful and powerful characteristics of a linear transformation, is that you can trust that it retains the basic shape of things. All it really can do is stretch it. Okie dokie, that was exercise 61. What is next in my little list of things to do? What is the time? Whoa, my goodness, we have 15 minutes left. What a lot of time. Okay, so let's see what... So that was still dots, okay? Those we were not... Sure, 4 of the dots were kind of in a line shape and 4 of them were in a square, but still we were transforming individual dots and we were seeing how those dots lined up. Let's now step up a little bit, and instead of transforming individual dots, we transform curves. Oh, I'm being very boring. I can see it on your faces. You're trying to be polite, but the boredom is coming through. Okay, so, dark blue. We can transform entire curves, not just individual points. The key, or the technique, or the important thing that you need to do is to express the curve in vector form. And once you've expressed it in vector form, you can carry out the transformation on it, because the transformation is framed in terms of transforming vectors. And I will demonstrate with an example, number 66. 62 and 63 are assigned for the next tutorial, and 64 and 65 are simply extra homework. You will find that this stuff is not obviously present in the textbook. So what's in the handbook is essentially all you've got. Unfortunately, yeah, I don't think I have a worksheet on any of this stuff. No. But there's a lot here. There's an awful lot here, and you'll discover that as I just did a jump now. I did a jump from 61 to 66, and I'll keep doing these big jumps because all the stuff in between is tutorial stuff and homework on whatever the previous little topic was. I'm being boring again. I can hear it in my voice. Here we go. So we've got a matrix. Hello, matrix. 1, 0, 1, 2, 1, 0, minus 1, 1, 3. Okay, apply the transformation represented by this matrix to A, a line, B, a plane, and C, a circle. Let's do that. Cool. I have 14 minutes. I can do that. The line x of lambda equals 1, 0, 0 plus lambda 2, 1, 2. And I did not write there lambda element of R, and I should have done. I shall write it here. Sloppy. Okay, so I'm going to apply the transformation to that. So here's what I'm going to do. I'm going to transform that point, 1, 0, 0, and I'm going to transform this direction vector 2, 1, 2. And the most efficient way of doing that is to basically do them simultaneously. I'm going to write the point as a column vector, and I'm going to write the direction vector as a column vector, and I'm going to allow them to share the same matrix, because why not? We know how matrix multiplication works, and those two columns are not going to interfere with one another. So I could transform the points in one calculation and the direction vector in a second calculation. Then I'll be forced to write my matrix twice. I'm very lazy. I only want to write it once, so I'll do it like this. Okay, matrix multiplication, yay! So what's that? 1 plus 0 plus 0. 2 plus 2. 2 plus 0. Oops. 2 plus 0 is 2, not 0. 4 plus 1. Minus 1. Minus 2 plus 1 is minus 1 plus 6 is 5. Unless I've made a careless error, that is the result. So let me just check my solutions. Okay, so basically what I have now is a new point and a new direction vector. And so the image of my line, so there's that word again, image, I'm still going to use x and lambda. If you'd rather not use lambda, you could use s or t or something. I don't really mind. In fact, in my notes, I think I used t. My notes I actually did use t. But
like x prime or something?
and so in this context, I wouldn't suggest a prime because it could be confusing somebody. Because in the context of this, it could mean differentiation. In the previous stuff, it couldn't. It was an unambiguous symbol to use, but here it would be ambiguous. I'd rather not use a prime. Yes?
Do we have to call it x because our original one is x?
No, it's just that's just our standard name for generic vector. But you could call it something else. I would sooner change the parameter if you wanted to make it look different to the previous one. I would change the parameter rather than changing the x. Question?
When you multiply the transformation into the
Okay, all right. So for the benefit of people who are very good at matrix multiplication but are just forgetful right this minute, if we want to do matrix multiplication, we'll take a row on this side and a column on that side, and we'll basically do a dot product. So it's 1 times 1 plus 0 times 0 plus 1 times 0, and that gives you 1, and we put it over there. We put it in the position. So I chose my first row and my first column. And therefore the result I get from the multiplication is going to go in first row, first column. If I had chosen, let's have a look, let's go for third row, second column. I would do minus 1 times 2, plus 1 times 1, plus 3 times 2, and the answer I get would go in the position of third row, second column. So matrix multiplication is basically a whole bunch of little dot products. Always a row of the thing on the left and a column of the thing on the right. You probably did some exercises in first year of showing that some matrices just can't even be multiplied. Because what if the row on the left has 3 components, but the column on the right only has 2 components? You can't do a dot product. It's a matrix, it's an impossible matrix product. Which is interesting, because it's the first time in your mathematical career that you encounter objects that are the same type of object but cannot be multiplied. Up until then, there's no such thing. Real numbers can all be multiplied. Natural numbers can all be multiplied. Functions can be multiplied with one another. But not all matrices can. It's bizarre. And of course, there's the lack of commutativity of matrix multiplication as well. Even if you can do A times B and B times A, they don't give you the same result. Again, it's the first time in your mathematical career you encounter non-commutative multiplication. Linear algebra is so much fun. It's so interesting. Golly. Sorry, getting carried away there. Let's get back to this. Okay. So there we go. We transformed a line. It was one line. It turned into another line. I have 3 plus 5 is 8. I have 8 minutes left. Let's do B, the plane. I've got a plane. Okay, now that plane has already been given in vector form. But just look down at exercise 68. There are 2 planes that are not in vector form. They're in Cartesian form. Do you know how to go from a plane in Cartesian form to a plane in vector form? We can do a little reminder of how to do that tomorrow morning, perhaps. In fact, no, let me do it right now. My plane has been given in vector form, so let me just write it out. But then I'll just do a little picture to show you what I would have done. Sorry, it's 2, 1, 2. What if I'd been given a plane in Cartesian form? What I would do is I would find 3 points that satisfied my equation of my plane, simply by inspection. I would look at my Cartesian equation and go, oh, if I substitute in 1, 0, 0, that point satisfies it, and how about 1, 1, 1? Yeah, that one as well. And I would just by inspection find 3 points. Of course, there are infinitely many points in the plane, so you should be able to find 3. So then what you do is you subtract them in pairs to get 2 little direction vectors. And you're done. Because then what you could do is you could take that as your point, and then you could take lambda times the one direction plus mu times the other direction. Let me call that R1 and call that R2, and R1 can go there and R2 can go there, and I'll call that A, and there's point A. Sorry, that's rather scruffy, but that's basically how you would go from Cartesian to vector. Find 3 random points well, not that random, because they have to satisfy the equation of the plane. Subtract them in pairs, that gives you your 2 direction vectors, and then choose any of the points, it really doesn't matter which one, as your point, and then your plane is point plus parameter times direction plus parameter times direction. Question? Yes, you do. Yes, you do. Excellent. Gold star for you. There you are. Question?
Is it just whether the normal faces up or down depending on which you R1 or R2?
Oh, it really doesn't matter. Really doesn't matter. Okay, so what I'm going to do is exactly the same as before. I'm going to transform the point, the direction, and in fact the other direction as well. And if I'm not mistaken, yeah, those first 2 columns are in fact the same first 2 columns I had in part A. and I do my matrix multiplication, and I'm running out of a little time here, so I'm actually going to be lazy and just copy it from my notes. That's a 1, 2, and a -1. That's a 4, 5, 5, just like the previous example. And then the last one is a 2, 1, 1. So what I have now is a new point and 2 new direction vectors. So image of plane is x, let's go for t and s. My point is 1, 2, -1. Parameter times the one direction plus parameter times the other direction. T and S element R. There we go. Here's an interesting thing that could happen but didn't happen here. Check to see whether these end up collinear. Check if these are collinear, or really, in fact, I don't really mean collinear, I mean parallel. Because it could happen. It could happen that we start off with 2 direction vectors that aren't parallel. But we saw in that dotty example earlier that lines are retained, but they change to different lines. So any direction vector could turn into a new direction. Well, obviously it's turning into a new direction vector, but there's the possibility that my 2 direction vectors, which started off non-parallel, ended up parallel. Not in this example, but it can happen. And in that case, it means your plane has actually turned into a line. So there's another thing linear transformations can do. They can actually decrease the dimension of something. They can take a plane and turn it into a line. They can take a line and turn it into a point. Question?
With parallel, you just erase the one variable.
Yeah. Make a note that they're parallel, and then you just wouldn't have to include one of them, because one of them, it's providing superfluous information that you don't need. Because remember what your direction vectors are doing in a plane equation. In a line, you say, okay, I have a point, I'm standing at the point, and then I go plus lambda times direction vector. It means I can take any number of steps that I want in the direction of my direction vector, and so I mark out a line. A plane says I have 2 direction vectors that are not parallel, and I can take any number of steps I want parallel to the one, but I can also take any number of steps I want parallel to the other, and so I end up marking out a plane of points that I can travel to. Still only 2-dimensional, not 3, because there's no direction vector taking me in the 3rd dimension, but those 2 direction vectors mean I can mark out a plane. So by them becoming parallel, I can only walk in a line. I can't walk in a plane. Okay, all right. According to my timer, I have 2 minutes. Let me do the last one. See, that's orange. I want orange. I want blue. It's a circle, right? It's the unit circle, perhaps? I've lost it. Yes. X squared plus y squared equals 1, where z is 0. So it's the unit circle on the xy plane. We need to turn that into vector form. In other words, we need to parameterize it. So this is cos t, sin t, 0. That is that curve parametrized. I could write it as r of t if I wanted to. T element probably 0 to 2 pi. That would make sense. So then I take my transformation matrix, 1, 0, 1, 2, 1, 0, minus 1, 1, 3, and I multiply it with the vector cos t, sin t, 0, and I get out something rather funny looking. I end up with cos t, 2 cos t plus sin t, minus cos t plus sin t. And what you should always try to do once you have carried out a transformation is to interpret what the image is. In this case, it's a little bit tricky to interpret. You look at that and you think, I don't know what that is. But if you sit there for a while playing with those, you can determine that it's an ellipse. Okay, this is an ellipse. It's not obvious. However, knowing what linear transformations do, it can only be an ellipse. Because the only thing that a linear transformation can do to a circle is keep it as a circle, or stretch it into an ellipse, or maybe shrink it down to a point. That's all it can do. And that's clearly not a point. It's an ellipse. You can do a little bit of fiddling. You can find that y equals z plus 3x. See how if you take z and you add 3 x's to it, you're going to get y. That's a plane, of course, is the plane the ellipse lies on. So you can fiddle with those and get a little bit of information out, but fundamentally what's happened here is a circle has been turned into an ellipse that we can't easily express in Cartesian form, so we leave it like that. Question?
How can you see that it's not a circle?
I can't really.
Like,
No, not actually just by looking at that. It could potentially be a circle, yes. I'm just going to finish off. Image of circle is r of t equals cos t, cos t, 2 cos t plus sine t, minus cos t plus sine t, and I'm going to keep t as element of 0 to 2 pi. I don't have any good reason not to do so. Okay, all right. So that's how you transform curves and surfaces, in fact. First thing tomorrow, I'm going to ask you to do number 67 and 68. That's quite a lot. You probably won't get through all of it by the time I move on. But 67, 68, and then what will we do? Gosh, what's next? Ooh, what's next is nonlinear. Yay!